So when I look at equation of a tangent plane of a surface, okay, let's say a surface of this form, if it's a function of x, y, z, or a function of three variables equals a constant, this is a level surface. We talk about it like level set, level curve, and level surface, right? So it's a surface described by an equation like that called level surface. Okay, so suppose I have a surface like this. Okay, it's being described by x, y, z equals 0. You can think about something in general. So for example, you can have x squared times y plus z equals 0. For example, a function of x, y, z equals 0 gives you a surface in R3. All right, and let's say now I have a point P of coordinates x0, y0, z0 sitting on the surface. Then I want to know that what is the equation of the tangent plane to the surface at this point. So what this means is, for example, if this glass is my surface and I put a point like this on the surface, then I say I want to find the tangent plane. So what is the tangent plane? It's a plane that you move from far to close and touch the surface and at that dot that I put on the surface. So this is the tangent plane to the surface at the point P. Okay, so we're looking for an equation for this guy. All right, so before we talk about equations and other fancy stuff, let's just think about it. So if I have any arbitrary curve sitting on the surface but passes through P, what do you think about the tangent plane and the curve sitting on the surface? You can imagine that this plane would also be tangent to the curve, right? Because they only touch at this point P. Okay, so this is my curve 1, and I can have another curve also is sitting on the surface, travel along, passes it passes the point P. Okay, so you can see that this tangent plane will again be a tangent plane to the curve at the P. Okay, so now you see that no matter what, if I have a curve on the surface, oops. So let R of t be, my writing is horrible, I'm sorry. So let R of t be a curve on the surface. And it passes through P. Okay? So it's like this curve or this curve, I don't care. As long as it's a curve, it sits on the surface and it passes through P. This can be one of the example. Okay? All right. So now what do we know then? We will know that then the tangent plane we talk about here, the tangent plane okay, so this is the tangent plane to the surface is also tangent to the curve R of t. Okay. So if you're okay with this conclusion, the tangent plane that I'm looking for, tangent plane of a level surface at P, would also be a tangent plane to any curve sitting on the surface passing through the P. Then this is what we can know from the statement, this conclusion. So if I compute R prime, okay, if I compute R prime, suppose this is my R of t, then this will be my R prime of t. Okay, then this R prime, this tangent vector, will be parallel to the, or you can say it's sitting on the plane. Okay, so think about this. Where's my surface? So this is my surface of the dot. If I have a curve going through like this, draw a line. If I have a curve, I don't know if you can see, I'm trying to show you. So if I have a curve sitting on the surface like this, okay? Now, when I differentiate this curve, I will get a tangent plane and it will look like this, okay? So this line segment, this pan, will coincide, will be parallel to, or you can say like it's sitting, not necessarily parallel, will be sitting on the plane like this, it's same direction. Okay, as long as it's not the glass that I drop, I'm fine. Okay, so we know the tangent vector R prime of t lies on the plane as well. Okay, and this is true, does not matter what the curve we're talking about. It's, as long as it is a curve on the surface and passes through the point P, then the tangent plane, sorry, not the tangent vector at P, okay, so this particular tangent vector at P, it also lies on the tangent plane, okay? And you can see if we use this other curve as an example, so let me erase this one. If I use this curve as an example, then my tangent vector will be like that. Okay, it's still sitting on the plane. Okay, so if it's sitting on the plane, what do we know? Suppose I have a normal vector. Normal vector meaning it's the normal that is perpendicular to the plane. Then I will know that the normal vector is always perpendicular to R prime at P. Okay? So this is a very important observation that we need in order to write down the equation of the tangent plane. Okay? So I'm going to make this normal vector a little bit smaller so I have more room to write. Okay, so now what I'm going to do is this. So I'm gonna consider a curve okay on the surface passing through P. Okay, and look at its composite function. Okay, so I will have f of x of t, y of t, z of t also equals 0, right? Because it's x, y, z is a curve on the surface. Okay. So next, I want to differentiate the equation. Which equation? This equation with respect to t, and let's see what happens. Okay, I'm gonna have to erase this graph. But again, this is the key observation that we had in the end. So keep this in mind, and I'm gonna erase as much as possible. Eventually, I will have to erase this as well, so then I have space to write. Okay, so I need to differentiate this. So this is basically f composite R in short, right? Okay. So I have a composite function and I need to differentiate this composite function. So you can say W is equal to f of x, y, z if you want to, okay? So W is a function of x, y, z. X is a function of t, y is a function of t, z is a function of t, because we now restrict on the curve. All right, so for us to find df dt, we apply the chain rule. So here you have dw or df, let's just use f, df dx dx dt. Okay, so this plus df dy times dy dt. Okay, so that's this plus df dz times dz dt. Okay, and now I'm going to rewrite this summation here using the gradient. So, okay, so keep this in mind. I'm gonna erase it. Okay. So this is equal to gradient f dot r prime of t. Think about it. What is a gradient f? Gradient f is the vector df dx, df dy, df dz. What is r prime of t? R prime of t, the formula is x prime. So that is dx dt, dy dt, and dz dt. Right? Okay? now I have delta f, gradient f dot r prime. So that will be df dx times dx dt plus df dy times dy dt plus df dz times dz dt. So you can see that this formula that we get from chain rule is nothing but gradient f dot r prime. Right? This is what we know from the chain rule. Okay? Moreover, we're differentiating an equation. So this is just the left-hand side of the equation. And the right-hand side, the root of 0 is equal to 0. So this is equal to 0. All right? So when we have a level surface and we restrict this level surface on a curve that passes through P, it satisfies this formula. Gradient f dot r prime equals 0. Okay? All right. So what does that mean? So this gives you tangent vector to the curve at P. And you have a vector gradient f that this tangent vector always equal to 0. What does that mean? That means at P, gradient f is perpendicular or orthogonal to the tangent vector r prime. Right? Okay? So gradient f will give you the normal vector. Okay? So we have a surface down here like that, and then we have a point P here. And we find from the formula, we find the gradient f at P will always be perpendicular to any tangent vector passing through P, right? So what does this mean? This means this vector here can help you to write down the equation of the tangent plane, because we need to write down an equation of a plane. What do we need? We need a normal vector. Okay? We have a normal vector, which is gradient f at P, and a point. We have a point. Which point? The point P, right? Okay? So now we just need to put the normal vector and the point P into the formula into the equation of a plane. Then we're good. Okay? So I want to, before I erase this, I want to summarize what we have so far. Starting from a given surface and a given point, then I say, okay, think about I have an arbitrary curve that's sitting on the surface and passes through the point P. Okay? Then we say, let us differentiate this equation with respect to t. So on the left-hand side of the derivative equation, I have df dt. On the right-hand side, I have the root of 0. So the root of 0 is equal to 0 derivative df dt. Using the chain rule, we know it's equal to gradient f dot r prime. Okay? So now let's look at what happens at the point P. So at the point P, r prime at P gives you a tangent vector. So like a tangent vector here. Okay? and it's arbitrary because the curve is arbitrary. It can go from here, it can go from here, as long as it sits on the curve on the surface and it passes through the P. Okay, so that means gradient f at this point P is always perpendicular to the tangent plane. The tangent plane we're looking for. Okay, so that means we found a way to find a normal vector of the plane. Moreover, because of the definition of tangent plane, we also have a point on the plane. Now we just need to put these two ingredients into equation of a plane, then we're good. Okay, so let me erase this. So conclusion, what? Gradient f at P is a normal vector to the tangent plane. Okay, so what is this? This is df dx at x naught y naught z naught, df dy at x naught y naught z naught, df dz at x naught y naught z naught, if I write it out. Okay, and 2, with the point P x naught y naught z naught, we have the equation that is gradient f at the point dot x minus x naught, y minus y naught, z minus z naught equals 0. Okay, so if I want to write it out, I can replace the gradient by what do we actually have for the vector. Okay, so let me write it out for you. So I'm gonna have df dx evaluated at P, okay, times the x component plus df dy evaluated at P times the y component of the vector plus df dz at the point times z minus z naught, and equals 0. So this is my equation